Welcome, everyone, to our talk. It's quite a long time that we didn't do an update of rust-vmm here at KVM Forum, so we decided to provide you some update. We are part of the rust-vmm community. I'm Stefano Garzarella from Red Hat, uoqing from Institute of Software, Chinese Academy of Science, and Patrick Roy from AWS. Let's give an introduction of rust-vmm for who of you don't know about it. Essentially, we are an open source project that provides building blocks for virtualization solution like VMMs and hypervisors. So why rust-vmm? Mainly, we want to avoid, we want to reduce code duplication. So, for example, if you want to implement a virtio device in your VMM, you can, we will provide to you a virtio implementation that you can use. So in this way, you can also increase the speed of the development of your solution. And of course, we are also focused on testability of our crates and security. And we want to provide a clean interface because we want to, essentially, we want that our crates are adopted by a lot of different software. And we have two main communication channel, a mailing list and a Slack workspace. I left the link here to if you want to join. And okay, what we provide. This is a list of our repositories and the crates that they contain. Of course, we are from the name you can guess that all of them are written in Rust. So mainly we provide wrappers to interact with hypervisor like KVM, Hyper-V, and Xen. We also have a Linux kernel loader. So if your VMM don't use firmware like OVMF, you can load Linux directly using this crate. And then we have a couple of crates for resource management, like the VM allocator for allocate MMIO addresses or device IDs. And then we have the VM memory, which is one of our core components used by, I can say, most of our, for example, device emulation code, because it's abstract the guest memory. And then we have, of course, as I mentioned, a lot of crates related to device emulation and I/O, like virtio abstraction for the virtio and the devices. We also have wrappers for vhost, vhost-user, and VDPA. We will go into it later. We have several devices, vhost-user devices that use those crates. And then we have a couple of crates for VFIO to pass through devices or virtual function to your VM. And also several legacy device emulation in the VM Super I/O crate. Other than those, we also have a couple of repositories for our ecosystem. The community one, which I already mentioned, that contain useful information. And then the rust-vmm container, which is a container that we use in our CI that you can use also locally to test your code. Now let's talk about who use our code. So essentially, we provide just the building blocks. We don't provide any kind of VMM, for example. And one of the first one that I want to mention is Firecracker, mainly because rust-vmm was born together to Firecracker when they essentially forked cross-VM. Another one, and Firecracker is essentially it's a lightweight virtual machine that they call micro-VM, and the target is a container workload. Another VMM I want to mention is Cloud Hypervisor, which is a bigger, we can say bigger VMM, mainly for cloud workloads. And they also heavily use rust-vmm crates and also collaborate with us, like the AWS guys. Another one is libkrun, which is a dynamic library that allows software, an application to spawn processes in a really lightweight VM. And use case is, for example, a container runtime for Podman is used, thanks to libkrun, is able to start container inside a Podman container inside a lightweight VM. And then we also have Dragon Ball Sandbox, which is a runtime for Kata container, which is also a lightweight virtual machine monitor for Britain, that partially use our crates. Other projects also related to that use our rust-vmm crates are, for example, vhost-user device. I have more slides later, but essentially allow us to move the virtio device emulation in external process, and they can be used by any kind of hypervisor that support vhost-user protocol. Then we have Imago from HANA that provide access to VM image format like QCOV2. And another one is vmexec, which is a command line interface that allow you to run command in a single command in a throwaway virtual machine. And also, I recently found also this other project, Nidus, I hope the pronunciation is right, from Dragonfly. So it's a Dragonfly image service. And they support FUSE and virtiofsd, and they do the virtiofsd protocol using rust-vmm crates. So this is essentially the main project I found that are adopting our crates. But I also want to mention other two projects which is related to rust-vmm. The first one is cross-VM. Most of our code is based on, a lot of our code is based on cross-VM code. Essentially, most of them was forked from cross-VM. And they also brought this statement, so they are open to use our crates, but still not the case. Another one is OpenVMM from Microsoft. They recently, I think they published last year, is a VMM for mainly for confidential computing, for confidential VMs. They use it as a paravisor, and they replace the C implementation with the Rust one, and they essentially mention us in their documentation, and they are also open to collaborate with us. So we are open to collaborate with both. Will be great to join the force on that. So let's see if in the next years we can improve the situation. And about the architecture we support and operating system, we mainly support x86 and ARM, but recently uoqing also did a great job to support also RISC-V. He will talk more about it. And about operating system, of course, Linux is the one that we really support in every crates, but some of them also works on Windows. And we are also doing an effort to support other POSIX system other than Linux, especially for the vhost-user devices, because essentially vhost-user, as I mentioned, allow us to move the virtio device emulation from the VMM to an external process. And this is inspired by vhost, where the idea was to move the emulation from the VMM to the host kernel for performance reason. In our case, in the vhost-user case, is more for safety, and also for you can also easily maintain your code or update your code on fly, and also your VMM can be written in a completely different languages from the virtio devices. And the vhost-user protocol is mainly based on the Unix domain socket. So we have a socket between the VMM and the application. And this socket is used for the control path. And for the data path, there is a memory shared from the VMM to the device. And the only requirement is that that memory should be addressed by a file descriptor that then can be shared. I talked this year at FOSDEM about if vhost-user can be used in any other POSIX system, and the answer is yes. And we did a Google Summer of Code this year on that, so I will talk about that later. And about rust-vmm, we support vhost-user device. We provide several crates. One is the vhost crate, which is a Rust library to abstract vhost, vhost-user, and VDPA. And then we have another one, which is vhost-user backend. That is a framework to implement vhost-user backend, which with front end, in vhost-user, we have the front end, which is the VMM usually, and the back end, which is the application that implements the device. We have a lot of devices implemented in our rust-vmm vhost device repo, like CAN, console, sound, video, vsoc. But also we have external one maintained by Hannah and Herman, which is the virtiofsd, which implement the virtiofs device. What we did recently in virtio and vhost crates. So essentially, we started to support live migration for vhost-user, mainly thanks to Herman. We started to support shared object for vhost-user devices. Essentially, in virtio, usually the memory is exposed from the guest to the host. But in some use cases like GPU or also maybe also DAX for virtiofs, we need to expose. We need the host needs to expose some memory to the guest, and this should allow these use cases. And then we also improved the way to reset our device, thanks to Anna. And Matthias developed read and writer classes to improve our way to process virtio descriptors. And when you implemented the packet descriptor in the virtio crate. What we are doing recently, so I put here 2 Google Summer of Code of this year that we are doing cool stuff. The one I already mentioned about supporting vhost-user device in POSIX system other than Linux. And it was done, still doing by Wenyu Huang. I put also a link to his final report with all the PR that most of them we already merged, so we are really near to complete this effort. And another cool one is the formal verification mentored by Matthias. And also it was done by Siddharth Priya. And another things we are working on is to improve the Xen support in a vhost device, but it's mainly depend also on the VM memory crate, and I'll let Patrick to talk more about it.
Yeah, hi, I'm Patrick. Yeah, as Stefano just mentioned, one of the ongoing efforts in rust-vmm is supporting the Xen support that we have for the virtio stack, and that is currently hinging on one of the more foundational crates for which I'm a co-maintainer, which is VM memory, which Stefano also already mentioned is sort of the crate that provides some abstractions for virtual machine guest memory. So it essentially wraps a bunch of unsafe code that one would normally need to write in Rust for dealing with like raw mmap pointers, and gives some like nice and safe abstractions over them that deals with all of the pitfalls of Rust's safety invariants when it comes to dealing with raw memory. And I'm just going to give a bit of an update over what has been going on in this crate in the last year. What are we currently going on? One of the first things we've done is we had a request from libkrun to make it a bit easier to use guest-memfd, which is this new memory management interface by KVM that's currently mainly used for confidential VMs. Make it a bit easier to use it with VM memory, because at the moment VM memory is very much tied to this model of each region of guest memory. For example, each KVM memory slot has a VMA associated with it, and all the accesses that VM memory allows to provide abstractions for accessing the memory goes through this VMA. But sometimes we also have some sort of metadata that we would like to associate with the guest memory. For example, if VM slot also has a guest-memfd, and libkrun folks on into some problems where just storing that metadata completely separate from the guest memory was a bit troublesome, where it would have been a lot easier if they can just like cram all of that together into the same guest memory region. And so instead of explicitly supporting guest-memfd in VM memory, which also would have been a bit complicated because obviously we also support Windows. We also want to support Xen, and there is no guest-memfd there. We sort of just generalized our sort of support for collections of guest regions. We say, okay, this is not generic. You can manage any sort of collections of guest memory as long as they implement a specific trait that defines all the basic operations that VM memory needs. And libkrun can use that to store the guest-memfd with each memory region. Firecracker is planning on using it for some memory hot plugging support to keep some bookkeeping about which regions of memory have been hot plugged and which not. So that's one of the things we've done this year, which we think should mostly work for most use cases. Then one of the things we're going to look at, which is what Stefano mentioned earlier, is better Xen support. This is a bit historically grown, so Xen has a different memory access model where you have grant mappings and foreign mappings, and right before you want to access your memory, you need to map it either for read or for write. And due to the way VM memory was originally written, there's a lot of sort of if-defery going on, where some of the core structs are defined differently for each of the different architectures, and the way Xen was implemented was, okay, we sort of treat it as a different architecture or a different operating system, even though it's not really, it's just Linux. But because this is now all if-def with the Linux, the normal Unix KVM code, what the vhost folks are forced to do is they need to have one binary with Xen support, one binary without Xen support, and we're slowly working towards untangling all of that and just allowing everything to be in the same binary. So there's a pull request open for that we're slowly working through. There is another ongoing effort by Hannah, which she's about to give a talk about right after, about supporting a virtual memory model in VM memory. Currently, it's completely a purely physical memory, so all of the accesses that you do to a VM memory object are interpreted as being done via a guest physical address. So if there's an IOMU, then you just can't really express those accesses, and so that's what Hannah's PR setting support for. Then, as part of this discussion, I found out that there's apparently some ongoing effort to potentially use VM memory in reusable. Paolo pointed that out to me, and I talked to a few people, and they were also not really aware of that. So I put a link there in case anyone else is interested in it. I think it's really cool. There's also 2 talks tomorrow about using Rust in reusable. So potentially that's going to come up there. One of them is by Paolo, so that's so good. And then there's a few just random ideas. One of them is we have this one type, which is essentially it's a slice of guest memory, which should just be a pointer and a length. So essentially it should just be an IO back. If it was an IO back, then that would make it really easy in virtual code to just say read, write, read. But it's not. There's some additional metadata in there. I would love to sort of get rid of it. We're not really sure how to do it. And then lastly, since Rust-vmm got started, there's been some effort in the Rust ecosystem in general to do safe transmute. So essentially, just like a reinterpret cast from C++, but in Rust for safe. And Rust-vmm has its own homegrown solution for that, which I would like to replace with the better tested one that the general Rust community has come up with, zero copy. We also have an issue for that. If anyone wants to do a good first issue on Rust-vmm, this one is one we would be very welcome for help on. Yeah, this is what's mostly going on in VM memory at the moment. Another thing, I'm a Firecracker maintainer, so I'm also looking at Rust-vmm through the lens of what would be nice to have for Firecracker. For Firecracker at the moment, it would be really cool if we had better support for ACPI and PCI in Rust-vmm. Currently, we have a crate for ACPI, but it's not on crates.io, so we can't really depend on it from the downstream to Firecracker. So Firecracker currently has that and blended it into Firecracker itself, which I would love to get rid of, so we could use the upstream crate. Similarly, Firecracker recently got PCI support. Here, we don't actually have any Rust-vmm code at all. Instead, we just took the one from Cloud Hypervisor. It would also be cool if there's maybe some interest in having some common PCI crate in Rust-vmm stream, maybe just starting with like some bindings, which seems like an easy place to start and agree on, and then maybe build on from there. Yeah, and lastly, one of the things we wanted to talk about a bit is some operational challenges for Rust-vmm. The current operational model of Rust-vmm is we have like 20-something crates, and some of them have very long dependency chains. There's a crate called vhost-user sysutil, and that has like a transitive dependency chain to like multiple other crates before it actually reaches the final downstream crates. And so whenever we do like a major release for vhost sysutil, we need to propagate this into a major release of the memory, do a major release of the virtio, do a major release of the host, and only then we can actually consume it in the final downstreams. That's one of the things I think is going to talk about a bit more what one of our solutions there is. But essentially, I think what we're going to end up doing is we're just going to merge most of our crates into just a single repository so that we can just do all of the version bumps in a single PR and just do all of the releases automated as soon as that PR is merged, instead of having to go through like 10 different crates. Because we keep missing things and then we have to go back, and it's just a bit of a mess. But uoqing is going to talk to us a bit about where we're at with that. How does this work?
Hello, everyone. I'm uoqing. And yes, just as Patrick mentioned, we have met a lot of operational challenges while we are trying to maintain rust-vmm crates. Namely, if like the example he just took, once there are change in VM and VM6 crates, we need to propagate the changes into other crates that depend on it. So there would be lots of PRs created in several repositories. So, well, actually, I'm still maintaining Cloud Hypervisor and Cloud containers, which those repositories are by themselves monorepos. So by watching and learning how the maintenance of those communities doing these maintaining jobs, so we come up with an idea to eventually we could have a monorepo including all the rust-vmm crates to manage them. I'm sorry, I'll need to start. These are the works we have done so far. We now have 4 monorepos by far, and we managed to merge KVM bindings into KVM outputs and renamed the repository into KVM. And we did the same thing similar to VFIO repository, VM virtualization repository, and vhost repository. Yes, but the end goal is, like I just said, we are going to have a monorepo for all the crates, but Rome doesn't build in one day, so we are moving on that direction already. So this is a blueprint of my end goal. It could be someday we could have a single repository named rust-vmm, which includes all of these crates we are maintaining. And by that time, we could use the Rust workspace to easily manage all the dependencies of each crate. The dependencies is shared by defining the workspace dependencies. And after all, we will reconstruct our CI infrastructure. We use path dependencies without version specification. So we can make sure our CI is actually running against the most up-to-date snapshot of the our working tree. So besides those, like Stefano just introduced, I was working on the rust-vmm on RISC-V architecture. I started this work I was trying to bring Cloud Hypervisor and Cloud containers onto RISC-V architecture, and I find out the crates in rust-vmm is lacking RISC-V architecture support, so that's inevitable. I need to work them out. To achieve this illustration is I drawn to illustrate some of the very important crates for a VMM for VMM to dependent to eventually boot Linux on RISC-V architecture. Before we can merge code into the core crates like KVM bindings, we first need our CI infrastructure to run the tests on RISC-V architecture, which is very hard because we do not have those kind of RISC-V hardware manufactured yet. This hardware either lack the H extension, which is the VTX extension in Intel or something like that. And we managed to use the emulated environment on x86 machines provided by AWS to run the simple build and unit tests for the rust-vmm crates. So after we launched RISC-V architecture support in the rust-vmm container and rust-vmm CI, these 2 repositories is the infrastructure of our community, and we can eventually move on to supporting the core crates on RISC-V. There are some links I put here, which showed the detailed work of how these crates are supported on a new architecture, namely RISC-V. So there are still a lot of work to do in as of RISC-V aspect. The first is we definitely want to use real hardware for the CI job. Unfortunately, we do not have them yet. So that's something I will try to address. Once our institute got hold of these hardwares, we'll try to connect these hardwares into our infrastructure and let them to take the RISC-V CI jobs. And of course, there are some crates lacking RISC-V support, like the vhost stuff, virtual stuff, and the VFI stuff. Yes, that's in my to-do list. I will try to support them and bring and write pipelines for the CI to make sure they works perfectly and correctly on RISC-V architecture. Yep, that's besides that, we have many VMMs that's using rust-vmm, like aforementioned Cloud Hypervisor, libkrun, and cloud containers, extras, and these hypervisors are taking Cloud Hypervisor as an example. Cloud Hypervisor currently now is able to direct boot Linux, and libkrun is almost able to boot Linux now. There are still GSI configuration jobs to finish, and we are there. And cloud containers is almost there. So that's it. That's all. Thank you. I'll give
Any question?
what emulation?
Just to repeat the question. So he was asking if we know if someone is working on IO epic emulation in rust-vmm, right?
So I think actually RTC, there's a little bit of support because Firecracker supports it. But I think because a lot of rust-vmm is born from Firecracker, and for Firecracker we said clean slate, we don't support any of this legacy stuff. We have a very minimal VMM. That's why there's not a lot of support for all of these other legacy stuff now. You could be if you want. we would accept contributions, definitely. Yeah, definitely. We would absolutely welcome contributions.
Like Cloud Hypervisor, for example, I think they target more, not only micro VMs. Right. Yeah. Okay. Yeah. If you want. Yeah, we are here. Any other question? Oh, okay. Yeah, essentially we already have a single repo for VFIO where it contains multiple crates. So VFIO binding is one crate, VFIO, I don't remember the names, is another crate, and we already have several repos that contain multiple crates. So our final goal is to put everything in a single repo, in a single Git repo, because the problem we have is once we update, for example, vmm sysutil, which is used by all of our crates, every time we forget something, because the other crates essentially needs to be that VMM sysutils publish on crates.io, and then we need to update and so on. So sometimes we forget something and need to do another release and so on. This is the main point. We are on. Okay, yeah, thank you so much. And yeah, see you.